Good morning, or whichever greeting matches your time zone. Welcome to this online session on water dowsing, the noble art of finding well sites. We want to tell you about how we no longer use a willow wand, we use hard science. And we, in this connection, is Aarhus University and the Grundfos Foundation. My name is Poul Due, and I work for the Grundfos Foundation. The foundation owns the pump company Grundfos and also has a philanthropic arm. Our largest areas of philanthropy are research, that's me, and water for the poorest, that's my colleague Niels Thorup, who's also present for possible questions in this session. Niels works through NGOs on setting up solar-driven water supplies in forgotten refugee camps and the surrounding host communities, as well as other last-mile villages in South Asia, Subsaharan Africa, where no business plan has ever set foot. When digging for water, we have experienced success rates down to 30% in some areas. And a dry borehole is a highway for contaminants. And it is $10,000 lost. And out there, dollars are precious. At Aarhus University, we found a technology that uses electromagnetic pulses to map the resistivity of the subsurface at a given point, down to around 100 meters depth. By moving the equipment around, you can build up a 3D map of the underground resistivity. Now, low resistivity typically means clay, high resistivity means water, means sand, and sand typically means water. So what we have done as a foundation, we have funded a ruggedizing of the technology. We've sent it to Tanzania with the people from Aarhus University, and we performed measurement campaigns in the camps of Nyarugusu and Induta and the surrounding host communities. Our goal is making the technology easy to use so that you don't need to have a postdoc in geophysics to interpret the data. So we also funded development of automatic real-time analysis of data. We have had an absolutely excellent cooperation with the university and with the NGO Water Mission. And I'll now give you the word to Dennis Kronbacher from Aarhus University. Thank you.
Good morning, everyone. Thanks, Paul, for the excellent introduction. And it's really great that we're still able to meet online, even though that the physical conference has been canceled. We can still reach some of our goals through this webinar. And today I'm very excited to share with you some information about a project that we're involved in partnership with the Poul Due Jensen Foundation. A project that for our research group is quite unique in that it's so implicitly balancing research objectives with contributing to meaningful humanitarian goals. Where the goals in this project, where at the core of this project is technology that make a meaningful.
Please turn off your microphones.
Sorry. At the core of this project is a technology that I think can make a meaningful contribution to enhancing the likelihood that we drill successful wells in data poor environments. And what I mean by a data poor environment is any environment where you have no pre-existing knowledge about local groundwater systems or processes. And the problem is that in these environments, it's quite difficult to drill successful wells. There's a very high failure rate commonly. And these wells can fail for any number of reasons. It could be that the wells are drilled that just simply fail to find any kind of water resources at depth, or they could fail to intercept water resources that are suitable for drinking or for irrigation. This could be the case if the water content is high in salinity, for example. And the problem with these failed wells is that they represent a significant financial burden, either to the individual or the community, or often the NGOs that are typically tasked with drilling these types of wells. It's a sunk cost that fails to deliver on so desperately needed water resources. And so anything you can do to enhance the likelihood that when you do drill one of these wells, it's going to be a successful well it can go a long way towards stretching the impact of projects with a finite budget. And so before we jump into specifics about the project or the technology, let me get a little bit of context on our research group and where we're coming from and why we think that the technologies that we work with are so well suited to solving these problems. So I'm a member of the hydrogeophysics group at Aarhus University, and as hydrogeophysicists, we're interested in trying to better understand groundwater systems and processes. And in particular, in our group, we're interested in trying to build tools capable of imaging what the subsurface looks like. It's okay. It's fine. And the type of things that we're interested in imaging is things such as, at what depth is an aquifer present? How thick is this aquifer? What's its lateral extent? How regionally connected is it to other systems? We're also interested in trying to locate things such as barriers to flow, clay layers, highly fractured zones, these kinds of things. We're also trying to give quantitative estimates of certain properties in the subsurface, things like the water content, which is of course important to trying to constrain the total abundance of water at depth, and also things such as how well can water flow in the subsurface. All of this kinds of information is very valuable in order to be able to give to a hydrologist in order to help them optimally site future borehole locations, or in order to better predict how these types of systems might behave due to some kind of change in external stimuli. In many ways, you can think of the role that the hydrogeophysicist plays in this groundwater framework as being quite analogous to the role that is played by the MRI or the CT scan technician in the medical fields, where they're also trying to produce high-resolution images, in this case, of the human body, that can aid a doctor in making an accurate diagnosis. Where the advances in these medical imaging technologies have really revolutionized the field. It's almost unheard of today that a doctor would order surgery for a patient without first conducting a suite of medical images to be done. And in many ways, this is the vision we have for these hydrogeophysical imaging tools. So our goal is to create tools that are well suited to rapid, cost-efficient mapping of the subsurface. And so this image here is one example actually produced with the technology that's at the core of this project, where from the ground surface, the system can be driven around, and in this case, in a matter of tens of minutes or hours, produce a very complex characterization of these 3D systems. Classically, the way that you would have to try and build out your conceptual understanding of what these groundwater systems look like would be to either perform geological mapping that's done at the surface, where you're trying to locate surface expressions of the geology, or you would have to employ boreholes or exploratory boreholes often, where you would actually be drilling boreholes into the subsurface in order to observe directly the properties at depth. And of course, this is the most accurate way of estimating what the properties at depth are, but it's also quite expensive and leads you with very sparse data sets typically, where you're left with information that's relevant at the location of the borehole, but that can leave a lot of uncertainty as to what the subsurface looks like as you move greater and greater distances away from that borehole. And so you're often left with these sparse data sets, and the result of this is that they often culminate in poor success rates for boreholes drilled in these kinds of data poor environments. And so geophysics, I think, is really well suited to filling this unmet need where you can rapidly map these types of systems, ultimately trying to improve the likelihood that you'll be drilling a successful well. And at the core of this project is a motivation to try and build technologies that can help solve water situations for the most dire of communities that are really suffering under quite stressed water systems at the moment. Just some cold statistics. So from WHO, UNICEF, it's estimated that about 844 million people globally currently lack access to basic water services. Basic meaning any water source that's coming from piped water or from protected boreholes or covered hand-dug wells or springs. And of these people, about 435 million people are collecting water from unprotected wells and springs, with another 144 million dependent completely on untreated surface water sources. So these are water sources at high risk of contamination. Often it can lead to elevated instances of waterborne illnesses, for example. And this is a problem that left unchecked isn't going to fix itself. The UN is estimating here that nearly half the world's population could be living in areas of high water stress by 2030. And so it's extremely important that we come up with cost-efficient solutions to address these types of mounting water problems, especially in the developing world, where rising populations are only going to further stress already stressed water systems. And so in many of these situations, groundwater represents an attractive solution to ensuring a sustainable and safe water future for these communities. And the reasons for that is that groundwater is often typically at lower risk of contamination than surface water sources. The ground itself often does quite a good job of shielding water resources at depth from contaminations that may be present at the surface. And groundwater is also potentially present in regions without access to attractive surface water sources. It may also be a water source that's more reliable throughout the year, especially in regions where surface water sources can be kind of ebb and flow between the dry and the wet seasons, for example. But it's somewhat easier said than done in certain cases to locate and exploit these groundwater sources. The first thing you have to do is find them, and the second is to put in the finances in order to be able to exploit these resources and build out sustainable infrastructure around these wells. So traditionally, the way that siting boreholes would be done in these data poor environments, again, environments where you have little to no pre-existing knowledge about local groundwater systems, is you would often begin either by viewing satellite imagery of the region. You would be looking for things such as surface water sources that may have connections to potential groundwater system, streams, rivers, lakes, ponds, these kinds of features. You're also going to often complement it with some surface-based geological mapping, again, looking for surface expressions of these geologies. But you're consistently plagued with this same problem where you have a lot of uncertainty pre-drilling as to the actual properties of the subsurface. And if available, you're often trying to bring in as much supplementary data as possible. And in these kinds of environments, and in particularly when we were working in Tanzania, all that's really available is either digital elevation maps showing you the topography in the region, or local knowledge where you're traveling around the town with local leaders and just looking at local water sources, basically, to gain any kind of insights into local systems. And this is really where near-surface geophysics can hit a niche. In these environments where you have little to no pre-existing knowledge, there's a need for these technologies that can, from the ground surface, without the need for drilling, be able to better constrain and inform what these groundwater systems look like. And just like in medical imaging, there's a number of different technologies, each with their relative advantages and limits, of course. So just as you have ultrasound and CT scan and MRI, in our group, we also work with a range of different technologies. But there's one that kind of, I think in this context reigns supreme, and that being transient electromagnetics. Change the slide, Paul. And transient electromagnetics is it's a workhorse technology in hydrogeophysics, really. It comes in a number of different flavors. All of them involve the use of a large coil of wire, either that's deployed directly on the ground surface by a 2 to 3 person team, typically. That's what's visualized here in this ground-based image. Or it's deployed on a rigid frame that can be towed behind an ATV or picked up by a helicopter and flown underneath the helicopter. And in all of these cases, they're at their core the same physical phenomena that's being exploited here to map what is the electrical resistivity structures in the subsurface. It's just different forms of instrumentation that can either prioritize large spatial coverage or cheap deployment effectively. And the way that the technology works, and there'll be a seminar later today at 3 p.m. that I also invite you all to join that will be focused much more explicitly on the specifics of the technology. But very briefly in this case, the way that the technology works is that you're pulsing very strong currents in these coils. And what these currents do is that they generate secondary currents in the subsurface, and the strength and time dependence of those currents can be measured by receivers at the surface. And then using mathematical tools called inversion, we can produce images of what the electrical properties in the subsurface look like. And then we can rely upon decades of literature and experience in order to convert our images of electrical resistivity into their likely geological identities. And the technology that we're most excited about in our group, and the one that is at the core of this project, is a system called TTEM, where the T stands for towed TEM. And it's a system that is towed behind an all-terrain vehicle, and it really hits a previously unfilled niche in hydrogeophysics, where you could have a tool that's capable of covering large areas, in this case, typically hundreds of hectares per day or in linear distance, driving anywhere from 50 to 150 kilometers per day is possible, production rates, of course, terrain permitting. But in this video here, we're seeing what the system looks like. So it's driven by an operator who sits on the ATV. At the front of the ATV is a small tablet that operates the system and is giving the operator real-time feedback as to data quality, even now with some of the developments that have happened in this project, also real-time imaging of what the subsurface looks like. But basically what's happening is the red frame that's trailing behind the ATV is pulsing these electrical currents, and then the white box at the end is measuring the currents that are induced in the subsurface. And we're performing about 800 to 2,000 measurements per second. And the end result is that we're getting a 1D image of what the electrical properties look like beneath the system, approximately every 3 to 5 meters. And then from this, what you can do is you stitch together many of these individual images in order to characterize these complex 3D systems. And now an example. So the system has kind of, in the last several years, entered a large-scale production mode in Denmark. It's been employed across Europe and in the United States, but it hadn't quite been pushed into the rugged, more remote conditions that were present in Tanzania. And that was really what kind of this partnership was able to grow, was to push the technology into these new kinds of applications and much more challenging settings, as we were very quickly to find out after the first campaign in Tanzania. And this campaign was done in partnership with Water Mission Tanzania, and they were able to provide us access to several of the host communities in which they have ongoing project, as well as several refugee camps in Tanzania, where we worked in the Nyarugusu and Nduta camps. And today I'll give, or this morning, I'll give a brief example from the Nyarugusu camp, and then later today at 6 p.m. there'll be a data session where we'll talk much more about some of the outcomes of this first Tanzania campaign. But first, I'll give an example from the Nyarugusu camp. Turn over. So in Nyarugusu, the satellite image shown here on the left, Nyarugusu camp is home to about 170,000 refugees, primarily Burundian refugees that came over 3 to 4 years following civil unrest in Burundi. And the camp today is does have quite extensive water systems in place, but they're not sufficient to meet the full needs of the camp. And the camp is still quite dependent on local surface water sources. And so there's a growing desire to get the camp more dependent on groundwater sources in order to lessen needs for the dependency on the local rivers, which have heightened contaminant risks and also place stress on the rivers, which are also relied upon for further downstream communities. But in speaking with the Norwegian Refugee Council, who operate a lot of the facilities in the camp, sorry, it's okay on this slide. We were told, just go back one. Okay, sorry. Well, we were told that given a future wave of expansion, they would likely grow the camp to the north. And so much of our survey was focused to the north of the camp. And in this image here, what you're seeing with the red lines is the regions where the system was driven. So these represent locations where we've driven this ATV system and actually been able to produce images of what the electrical properties are at depth. And in the video that was playing, you can see what this system looks like in practice. It's actually, we draw quite a crowd when we're driving around in the camps. So it was essential often to have security that was with us that could help us deal with the crowds. But one of the positive outcomes was that working in these non-electrified camps or the non-electrified communities is that we're still able to produce high quality data within the interior of the camp itself. So it's not a technology that's necessarily limited to working outside of the communities. And the end results of these kinds of surveys are images that look like this. So this represents a 3D image of the local hydrogeological systems surrounding the Nyarugusu camps. So in purples, we're seeing a geological unit that's interpreted to be laterite at the site. In blues is a saprolitic layer that's clay-rich. And what this allows us to do is, when complemented with supplementary information that's available from some of the boreholes in the camp, we can build an interpretation that there's likely to be an unconfined aquifer system that sits atop of this blue layer to the north of the camp. And then at the base of that blue layer, there's also a confined aquifer system that's currently being exploited by a number of boreholes in the camp. And so images like this give you a lot of confidence that if you were to expand and potentially drill boreholes to the north of the camp, you could expect geologies that are quite similar to what you've already encountered in other regions of the camp. So it gives you a lot of confidence that if you were to employ a similar drilling strategy, it's likely that you would encounter the same aquifer system and find some high producing boreholes in these areas. But these represent the data products that are able to be produced by highly trained geophysicists or people who are working with this kinds of technology day to day, and really at this point, some of the people that are developers of this technology. And we see this as a key obstacle for wider adoption of these kinds of methods. And something that is also at the center of this project is trying to make these technologies more readily accessible to a much wider community of end users. If it's going to be restricted to being operated and interpreted by highly trained geophysicists, it's always going to limit the potential footprint that these kinds of methods could have. And so a big part of this work has been trying to automate as many of the manual steps in the data flow as possible. And this big part of this is basically automating the entire data chain, trying to restrict all of the manual steps to simply interpretation at the end. And one of the products of this has been a live inversion framework, where this here is an animation showing you what the operator is seeing during the survey. So the operator in the top left image is streaming on a satellite image their current location as they're driving around. You can superimpose any satellite beams you'd like. So in this case, the purple just happens to correspond to land that's owned by one particular farmer. In the right panel, it's streaming data live to the operator as they're collecting data. This is very valuable in terms of quality control and ensuring that your time in the field is spent most valuable, or your valuable time in the field is spent appropriately, ensuring high quality data collection. And then at the bottom ribbon, as it's streaming to the left, this is showing real time what the images of the electrical resistivity structures look like. And then at the end, a data file is written that can be read into a relatively easy to use software in order to produce those 3D animations, really kind of immediately deliver very high resolution 3D characterization of these groundwater systems. And then finally, I'll leave you with a summary and our long-term vision for the technology. Much as advances in medical imaging have revolutionized the medical field and play now a key cog in the workflow for any kind of invasive operations in medicine, we view these hydrogeophysical technologies as having the same potential, where they could play a key role in pre-drilling characterization of these kinds of systems, ultimately trying to enhance the likelihood that you're drilling successful wells in environments where you don't have a lot of pre-existing knowledge. And then I think to realize the full potential of these methods, there's going to have to be a lot of work done towards making these technologies more accessible to non-expert end users. And the big step in that is going to be automating as much of these kind of experience-required manual steps as possible. And with that, I think we'd like to open it up to a Q&A portion of the talk.
Yes. So we have one question already in the chat from Louisa Biscard. She asks, how can we ensure that the groundwater resource does not dry out? And I think maybe
I'll take that.
Should ask Poul to take that.
Yeah. Actually, we are so happy with the collaboration with Aarhus University that we are currently expanding this to build stationary surveillance equipment so that you can have a real-time measurement of the aquifer levels wherever you set up your equipment. So we can make that sustainable. We work on that.
Can I just put? One of the other things you often say, I have to take those one off because I can hear an echo. One of the things you quite often say is that when you are in Sub-Sahara, you don't have an environmental problem with groundwater. It's more a financial issue that you can't get access to the groundwater. Many places in Sub-Sahara, it rains a lot, but it's only a few times per year. But the groundwater is pretty sufficient because people are living very scattered in those areas. I hope that is also a part of the answer.
Okay, I have a question from Ridishi Soni. Ridishi asks, as this technique is field-intensive process, do we have any scalable model for the same?
The scalable model, meaning, I guess, so the methodology right now, with a 2-person team, you're capable of mapping tens to hundreds of hectares per day. And so this Tanzania campaign, it was a 3-person team with support from Water Mission. But in 10 days, we were able to map upwards of, I think, 300 kilometers of linear data. And this was enough to get quite high resolution characterizations in 5 host communities and 2 refugee camps. And I think in terms of scalability and having more systems in the field at any given time, that's something that I think is now ramping up. So there's a spin-out company that's going to be offering commercially these types of services, and these kinds of things will be more widely accessible. What was previously prototype instrumentation being used in a research environment is now kind of making that transition to more commercially available systems.
Does that answer your question, Ridish? Okay, great. Frederick asks, could this be deployed on an airborne drone?
That's a great question, and also planned research activities that are also done in partnership with the Poul Due Jensen Foundation. One of the big realizations from doing the Tanzania campaign is that even having the mobility that an ATV affords, you're still quite restricted in terms of land access in many cases, due to either brushy terrain, very rocky terrain, non-flat terrain, where I think a drone can make a lot of contributions in those respects. And so that's something that is, we're very excited to kind of have it be a big part of our research program in the next few years. So check back in a few years, and I hope that we'll have functional drone systems.
All right. I don't have any more questions in the chat. Is there anybody out there who would like to ask a question? All right. Then, here we go. There's another one. Can we estimate water quality?
Yeah, so that's one advantage of the EM methods, or the TEM method in particular, is that it's particularly adept at differentiating very fresh water from very saline water. So saline water typically corresponds with much more conductive results in the imaging, whereas fresher waters will correspond to much more resistive results. So that's one kind of very strong imaging target in TEM, where we're very well suited to mapping salty versus fresh.
Could there be any other qualities of water that could be explored with the technology?
That's an excellent question. It would have to be a contaminant that corresponds to a strong impact on the electrical properties of the formation. And so it's generally been salinity that's been the driver, kind of good, poor, salinity, fresh. Those are the primary water quality issues that can be differentiated with the TEM.
Okay, thanks. All right, here's another question, and it's very technical, from Ahmed. How is more reliable using ABM SAS 4000 technique for groundwater investigation? Mostly we can produce 1D model. I'm not sure I get the question, but maybe you do.
Yeah, so I think there are many systems that are capable of doing EM measurements, these kinds of near surface mapping. Where I think that the TTEM has an advantage is it's a system that can be rapidly deployed for relatively inefficient, that can map very large areas. These ground-based, man-deployed systems that aren't towable, they're capable of producing similar results given significantly more manpower, basically. So I think in terms of keeping costs down and mapping large areas, the TTEM is the clear winner compared to the ground-based solutions.
All right, so Frederick Roy Midgard asks, are there types of geology, e.g. minerals, that will cause invalid measurement data?
Yeah, there are many possible influences from different minerals. So the driver for this technology in the 60s and 70s was the minerals industry. So they drove kind of the push for large-scale airborne surveys, and it's still a workhorse technology in mining exploration. The shift towards groundwater focus has really been in the past 2-3 decades, but there are certainly strong influences if you're working in areas that may have ore deposits or other kind of more exotic effects. But generally, at least in the Danish setting, Northern European setting, it's mostly in the top 100 meters mapping units that are relevant for hydrogeological characterization, and it's less common that you would find something more exotic that they're looking for in mining.
All right. Dish Sony asks, how is it different from GPR?
Yeah, that's a great question. So GPR and TEM are both electromagnetic methods, but they have very different frequency bands. So you can think of GPR more along the lines of sending a pulse out and it bouncing off an interface and coming back, quite similar to seismics, if you're familiar with seismics. TEM does not work in that way of kind of this sonar sending and bouncing signals. We're measuring a signal that is from this migrating current density. So it's different limits of the wave equation, basically. So they're maybe complementary technologies, but not quite the same. And I think in terms of groundwater mapping, the TEM systems are probably better suited to giving you the depth penetration that we're typically interested in, down to say 50, 100 meters. And also they're quite adept at tracking these structures over very large areas. Where GPR has advantages is that it's really good at giving you very high resolution depth to those boundaries between layers.
All right. David Walker would like to know, you mentioned that it's a rapid deployment system, but how did you get it to Tanzania? Does it have to be shipped?
Yes, that's true. So the entire system can be fit into one pallet that weighs approximately 300 kilos and can be transported by a truck to carry an ATV and then a small trailer to carry the system once assembled. But in terms of shipping, it can be compressed into a single pallet. But it's, I guess, like any significant system, requires shipping, of course, to the sites.
Okay. I have no more questions in the feed. Does anyone else want to ask a question? Nadish Soni asks, how do you work it in densely vegetated regions?
Yeah, that's a great question, and quite frankly, a limit of the current system, in that if you can't drive through with an ATV, you can't take the system through, is kind of the long and the short of it. So we've worked in South Africa in very brushy terrain, where you could drive through with an ATV and bring the system with it. It's really trees and large bushes that you can't really drive an ATV through that are kind of the limit. And so in certain circumstances, that was quite a limiting factor, forests, brushy terrain. And so this is where I see the drone systems having a big impact.
All right. Again, we're out of questions. Anyone else wants to have a final question? Okay, it doesn't seem to be the case. Then I'd like to thank you for your attention, and maybe we'll see some of you again for the 3 p.m. session on the technology. Thank you very much.